Okay, so I'll start and then Kanghang will take over. So before I do that, I need to thank my many sponsors who've been supporting our NILM work indirectly. The reason I put this up, so we've done a lot of NILM work at Strath within broader applications. So it's not NILM just for the sake of NILM. It was for providing energy feedback, for assisted living, for food life cycle analysis to give accurate modeling of appliance life cycles, building measure accuracy, and so on. And it made me understand that there is a varied requirement for NILM across the sector, and we need to have some good evaluation methods and understand that take the user requirements into account. So the bottom line is there is high interest in appliance level feedback from a range of sectors, not just smart homes, but we need to meet end user expectations. So we've seen that if the feedback is inaccurate or it's not really properly quantified, if I say I get an accuracy of 50%, that's not really what a customer wants. You know, I can't say I can disaggregate your fridge at 50% and they'll be happy with it. We want to make sure that it's reproducible, it's consistent. Every time you run the algorithm, you're going to get a similar type of accuracy. So we want to minimize credibility issues with your end user if we want NILM to take off. So the first thing to do, you've got someone coming up with a data set, they want to try NILM. Well, let's manage the expectations. Let's see what can we disaggregate. We can't disaggregate everything, and we all know that. For a given house or building or a data set, what loads can we reliably disaggregate from smart meter data or from multiple meter data? What kind of granularity do you need? Do you need to meter megahertz, kilohertz, second to minute? And what kind of accuracy would work for you? Okay, so we want to be able to say, well, we don't want to say, well, it works well. That's not good enough. We want to be able to quantify certainties and uncertainties. Okay, and in order to do that, we want to be able to, lots of NILM approaches suggested, we want to be able to evaluate it on multiple data sets because different data sets vary considerably, and not just for 2 weeks, for a day, for a short period of time, or on ideal test windows, but for a long period of time. So a nice emulator would do that, and we can benchmark all algorithms and have a true perception of how well an algorithm really works. And no algorithm is perfect. What kind of situations the algorithm works well for, on what kind of appliance. We don't want to just see that, well, it works 90% for that house, but you know, for that appliance probably it works very well, but for others not so well, and so on. So quantifying these. So the key thing is then what are the most useful measures of NILM accuracy for all algorithms? There's quite a few out there. There's no one metric that's perfect, so we want a combination of different metrics and people keeping adding new things, so hopefully that will be embedded in the emulator as well. And we want to be able to present these metrics in a meaningful way. So if I go and tell a client, for example, our NILM can give you an F1 measure accuracy of no less than 70% if we use a 2-month testing period, well, you know, that's exactly what's going to happen. I don't know what that makes sense. I want my client to say, well, understand, yeah, I can reliably disaggregate that, and I've got the statistics, but I'm not going to explain it in this way. I'm going to give you a nice visual form, something that makes sense. Okay. Another thing that we've been recently trying is, given a data set, even before we run the NILM algorithm, is to estimate what the accuracy will be. So that's what Kanghang will be talking about later. So we don't try the NILM algorithm and then realize of putting all the resources in that, well, it won't really work for all appliances in this data set. We might get a good perception of how it would work. So there's been discussions on what are the popular measures of accuracy for event detection. We want to be able to benchmark different algorithms across the sector. So we, you know, if I run it on this data set, I want to be able to know that this algorithm on this data set works with this kind of measure. So this is what's been popularly used in the literature. There are 2 types of accuracy. There's classification accuracy. So that's drawn from the machine learning community, and it detects events when an event happened. And there are variants of those, but these are the key ones, your F measure. And I like to break it down to precision and recall because it gives you a true perception of what you can or cannot disaggregate. So there are good and bad sides to using these kind of measures. It's useful for applications which you need to know when the appliances were running. So, but it doesn't give you a measure of how much energy is consumed. Now, there is some different in the literature for multi-state appliances. How do people work out classification accuracy? Do you work it out on all states, or if I classify the washing machine, which has multiple states, do you only look at the high state, or do you look at those states as well, combine them? And sometimes, it's not very clear in the literature, and we need to make that clear. There are also synchronization issues when comparing with ground truth. So is an effect correct up to 1 second within a window of 5 seconds when you're working the ground truth? And I guess that will have to be embedded in the emulator. And it can be misleading if you present an F measure and there's only a few runs of that appliance in a data set. So we've been trying it out on red data set where there are few runs of the oven or oven, yeah. So for example, or stove or something, and you see a very poor performance accuracy, and well, that's not really meaningful unless I have a statistical enough number of runs to be able to compare. So FM in its own right is not intuitive. Precision and recall can be a bit more meaningful. Do you want to break it down to that level? So precision tells us how sensitive a NILM algorithm is at picking events. So it's at the top here, the true positive, the event actually happened over all events actually detected. Or you can go for recall, that the event happened over all events that have actually happened, true positives and false negatives. I think the latter is a little bit more similar to ACC, so we want to know how much I picked out on what actually happened. Then there's a second set of accuracy metrics, again, kind of popular. There are variants of these, but these are kind of the core ones here. You've got RMSC, MAE type of variants. You've got your ACC called TECA or various variants here. But again, all it compares your estimated power usage of the appliance that you disaggregated over what was actually used. And that's useful if you want to find out how much your appliance is actually using that you can disaggregate. So it's intuitive, especially if it's presented as a function of time. So again, you can say I have an ACC of 0.6, 0.7. Doesn't mean much if you say, unless you say, well, your refrigerator accounts for 6% of your total energy consumption for this month or for these 2 weeks or whatever, because the results will vary depending on the window of time you've tested it. Okay. There are drawbacks to that as well, because the errors can average out. So it could be on one day you underestimated your SEC, on the next day you overestimated, and then they kind of cancel out, and then you get a good ACC measure. So, everything is not perfect, but with a combination of metrics, we can get a true feel of an algorithm's true performance. So, given that, do we design our NILM algorithms to achieve high scores in classification accuracy? I guess in the community, we want, when we try an algorithm, we want to see how it compares with our F1 score, our ACC, or whatever, just to make sure it works well. But then you might limit yourself to that kind of accuracy measure. So it's nice to have a range of accuracy. So people should not just look at the NILM algorithm, but work on the NILM accuracy measures as well. I think it's nice to see that there's different measures. So I'll just look at some approaches to give you a feel on how these different accuracies vary. So we've been working on the NILM project on NILM at Strathclyde for 5 years now. So we've tried and tested and developed a range of algorithms, supervised and unsupervised. And I want to be able to evaluate them properly on a large data set and truly compare them once against each other. We released the raw and clean refit dataset for refit dataset, which is a true dataset which contains how people really use their appliances. So it's fairly noisy compared to the red dataset. It's over 2 years, over 20 households. People were monitored doing really their normal activities, under no test conditions. So I think it's a nice way of evaluating any algorithm. So the way NILM works, there are two kind of key steps. There's the physical signal processing bit, the bit that nobody really talks about, where you do the data cleaning or your median filtering and your pre-processing of all your data before you feed it into your clustering or your classification and all this stuff. that should probably also be embedded within any emulator. And then you do, if you're doing event-based detection, you detect your events. It happens so and so time before you do your feature extraction and your classification or pattern matching or whatever it is that you're doing. Both parts are important, and people should be talking about the pre-processing as well, because we're all doing pre-processing. We're all cleaning our data, preparing it in a way that would work for our algorithms. That should come out more as well. We've been using GSP because it's a new way of graph signal processing where you can map your data series, time series data into a graph. It is not probabilistic, so you don't need to have good clean data. You don't need to have lots of data. It works quite well, and you can work down into detail different aspects of the time series data and understand the signal a bit more. I won't go into details, but Kanghang will discuss that in more detail later on. But this was just to explain to you that besides median filtering, it is important to do the pre-processing. So here we've been tackling the problem that if you're looking at 1 second data, you get slow transients that come up as multiple edges, and that can actually confuse your event as multiple events happening. So this is an example of your fridge freezer and your dishwasher. So if you look at the dishwasher, for example, you've got a slow transient going up here. You would pick it up as 2 edges when really what you want to do is be able to pick it up as 1, because that's when the event actually happened. And it's the same case for if it keeps going up and down. Well, you want to kind of make it neat and nice into manageable edges that would still give you a true measure of when your event actually happened. So we're trying to smooth the data out. In the fridge, we're just removing your spikes, which can skew your data. So multiple events and edges are mapped and smoothed into 1 or 2 manageable events to give you makes the algorithm a bit easier to work with. So this just gives you more example on how it works. So for example, for the washer dryer, there were multiple edges, that's the blue ones, and we managed to isolate it into, so that's negative, it's just a symmetric 2 nice states of the washing machine, as opposed to you'd get multiple states and then you try to cluster them and you get multiple clusters and it will be harder to process them. So if we clean the data, manage it, pre-process the data a bit more, you can make life easier for your NILM algorithm. And that was the same for the washing machine. There are multiple states that you can manage it into a decent amount of edges. So how do we evaluate it? Well, most of evaluation that we've done is on the RED and refit data sets. RED primarily because that's what everyone benchmarks, mostly everyone benchmarks with, and we can compare it with the literature. And the refit data set, which I think is very nice because it's a good representation of what happens in real households with lots of appliances running at the same time and people doing different things at different settings and so on. So I'm going to present to you results that we've obtained for a couple of supervised, including our early work on CNN, deep learning for NILM. So just an example, this was done for Red House 1. All the data that we had for Red House 1, so that was a month equivalent, but because there's lots of gaps in the data set, it's equivalent to about 2 weeks of data. And this looks at all appliances in the house. So we looked at FM and ACC measures, so classification accuracy and estimation accuracy, because both are needed to give an idea of when can we get the time series when the event happened, and as well as how much is your consumption accurate. So you can see that for most algorithms, you know, if an appliance works well, it tends to work well for most algorithms. So the supervised USP approach tends to work the best in most cases. The unsupervised algorithm is not so far behind, so there's still good possibilities for unsupervised algorithm, especially since we won't necessarily know what's in a house. We don't need an appliance survey, so that's quite a good approach. Then we've got a basic decision tree approach, which is simple and intuitive to implement. And we have the factorial amendments here that we got from the NILM toolkit. So Different measures of, so the oven and the washer dryer were probably not picked up because there were not enough sufficient good quality training clear data. But we get good accuracies for the oven, good accuracies for the washer dryer. For lighting, not so much. I've highlighted these two because generally you see that the FM performance tends to be worse than the ACC performance, but it does vary per data set, but this is what we've observed. Again, a measure of both of them gives you a good indication of how good an algorithm is and what kind of appliance it works with. So this kind of algorithm works well for maybe the dishwasher, but the UGSP works well better than for the fridge, for example, unsupervised, and so on. So we did the same thing for the refit house. So that was at 8-second resolution. That was done over a full 30 days. And for the supervised approach, we only use 3 days for training. We want to minimize the number of days that you need for historical data to train because it makes it not so usable. So again, we've got results for FM and ACC. Again, dishwasher tends to work well. We could have good accuracy, so it's not always a supervised GSP that works well. So the unsupervised case also works quite well. But if you look that there's quite a big gap between your FM and your ACC measure, if you look at the DT algorithm, for example, so that's 0.73 and that's only 0.35. And again, it could be, we need to look at the accuracy metrics, the number of FPs there were skewing things up a bit. So your fridge freezer, mixed performance. So even if it works well here, it doesn't necessarily work well on the other data sets. So different data sets give you different performance even for the same appliance because most households do not have the same appliance. They run a different, people open and close door fridges all the time. They can run at different efficiencies, different appliance labels owned by different houses. They all have different signatures. So we can't generalize that all fridges are good or all kettles are good at being disaggregated. Well, kettles are nice, but microwaves and so on. It does vary quite a lot. So you can go from 80% accuracy all the way to 40% accuracy. And that's a washing machine, which actually did better here. So different data sets, different results. Another thing that we also think is important is you need to be able to see how much of the total aggregate usage in a house your algorithms can disaggregate. So when looking at that, this doesn't look very good. It says 73% actually is not being disaggregated. So because we don't have ground truth possibly, but because we couldn't pick up the edges, and it's also a good way of testing, well, can you possibly look at the noisy, this is a noisy data set, there's many unknown appliances in that house, and this is what we can pick up. This is a bit more recent work on our deep learning. So we use a CNN approach. We tested it on red houses. So it was trained on all three red houses, I think, and tested on all three as well. And we did the refrigerator, the dishwasher, and microwave because they're present in all the houses. The good thing here, we only try to keep it simple as possible. We only use 10 epochs. We want to keep it simple just to see what the errors were. Metrics, so we've got our ACC here. Because we were using a regression approach, not a classification approach, we didn't use the F-score, but we've used the other type of measures there to give comparable accuracies. So this was the refrigerator for the red house. So just to give you an idea, so the yellow here is your aggregate. The green is your individual appliance, your submetered. The red and the purple are your estimated average use. So the only feature that we used in our algorithm was the average power for that appliance. So in this case, it works quite well. So you see the predicted and the estimated to what we trained was spot on. So you get a good accuracy compared to our SGSP, which was the best for the Red House 1, which had 91% accuracy. Promising. For the dishwasher also, we had some positive results. Slightly better than the SGSP. Again, same story. So, but you see here now that the real versus the predicted, there's a slight gap, but it was very close. So that's why it's slightly worse than the fridge, but still very good. And then the microwave, again, good performance, slightly better than our best performing ones. That doesn't mean I'm not advocating that deep learning is the best. We still have a lot to learn from deep learning. It has to be evaluated at scale. It has to be trained on the right amount of data set, but it should not be discarded immediately. There's lots of possibilities. So just to summarize that, we need a combination of measures to accurately disaggregate and benchmark algorithms. They need to be evaluated over a reasonable period of time when there are reasonable runs of an appliance. 2-3 runs of an appliance, that does not constitute a good way of measuring accuracy. It's also important to see how much you cannot estimate from a data set. Probably you won't show that to a client, but it's good for yourself to know so that you can improve your algorithm. And it's also important to be able to visualize that and not just tell someone, well, this is a table of how well I perform, and well, doesn't mean much to most people. We've been more recently challenged to work on very low data rates because many smart meters around in Europe measure up 10 seconds, 10 minutes, 15 minutes, up to an hour. That's the data that we have to work with. So that was part of 2 projects we've been involved in, the Sensible and the EcoBot projects. So you're getting data at 15-minute resolutions in research buildings, or in tertiary buildings, you get from 5, 15, 30 minutes resolution up to an hour. So the problem is quite different. You have to work on a different kind of feature here. It's a little bit trickier. So we've done some initial results. So we've used Coulter Sparks coding, which worked quite well. And we've implemented a simple kind of clustering using additional site information, environmental information to get some good results. So with KNN, we use additional features. So here we were not looking at environmental features because we're signal processing people. We like to understand our signal nicely. So we try to first start with our signal. So we look at the variance, the duration, the distance between cycles, number of peaks, when does it switch on, when does it switch off, this kind of thing, just purely based on the signal. And these are the additional features we use in our clustering. And these are the kind of results, again, for RED and refit data sets. So we've done well with the refrigerator. So 85% accuracy is quite good. Kitchen outlet, not so good, but the FM measure is good for the KNN. So again, different algorithms work differently well. This works nicely because we were looking at the mean, the variance, and other side features. Fridge, freezer, washing machine, again, reasonable performance. So, you know, this was done at 15-minute sampling. So we downsampled the red, well, not downsample, we worked out the consumed energy. Oh, okay, so I'm running out of time. So we're making a case that it's difficult to benchmark an algorithm. Metrics are different, data sets are different, your sampling rate all affect your NILM accuracy. So we want now just to be able to show how we can estimate accuracy for a house. So if someone comes to me with a data set, prior to running the NILM algorithm and doing all the steps involved, which is quite expensive, can we estimate accuracy and relate it to a metric? Yeah.
So we want to estimate the viability of disaggregation for an unknown data set given to us before we actually use our NIM algorithms, no matter how, what kind of algorithms we want to use. So, so that we can provide final results with certainties. So, like I say, I'm pretty sure that I have correctly disaggregated your appliances like washing machine, dishwasher, but I maybe struggle with toaster and microwaves, meet some problems. So the idea to achieve that is to explore GSP graph features and analyze them in frequency domains. The small energy in high frequencies and high energy in low frequencies will suggest that we are more likely to have correct classification results for them. The only input data we needed is appliance signature surveys, usually obtained from the time diary record by the users and the aggregate data. There are some primer work on the estimation part. but most of them are NILM algorithm dependent. So they did after their NILM algorithms, and they have no quantification that map direct into their accuracy metrics. So I will introduce a little bit about the graph signal processing here. In GSP, we associate power changes between samples from aggregate data with the graph nodes V, which is the green point you see in the figure here. And we calculate the weight between these nodes. This weight also represents the similarity of between the graph nodes. And we calculate the graph Laplacian L as the equation here. And we apply the graph Fourier transform GFT to analyze the graph signal we built in frequency domain. And the eigenvalue of L, which is the lambda on the diagonal of J here, will act as frequencies in the GFT, which means the high value of lambda will means low frequencies, not exactly frequency, but the similar informations. And we defined the graph signal according to the event detection results from the appliances service. And here is an example. The left figure shows that a graph for correct classified signal. You can see the left point red nodes are associated with the event has detected for an appliances from the appliance survey data, and the blue points are for the event not detected. The age between them are weighted according to the similarity of power value of those nodes. And you can see there is a stronger connection inside of a class and a weak connection between them. And the right side are the frequency performance for the GFT, and the GM hat here is the energy over that kind of frequency, which we obtain from the eigenvalue lambda of L here. And as you can see, there will be high DC components if all red nodes are connected with large weight, which means a good correctly classification results. So here are examples for frequency analyzed over appliances. The above two appliances has their energy concentrated in their low frequency components, and we will expect a good classification or disaggregation results for them. And as you notice, there are some high frequency components for them, which is caused by the similar power draws from other appliances or the noises in the measurement. We will expect false positives when we do the disaggregation. And for the below two appliances, more energy are concentrated on the high frequency. We will expect these two appliances will have worse results comparing to the above two. And we also compare two washing machines in same data set, different houses. We will definitely expect better results for the left washing machines for energy concentrate on the low frequencies. And again, two microwaves in red data set, we will expect better results for the right microwaves. And by comparing with the ground truth we obtain from the submeters, our estimation is correct for these appliances. And here is how we quantify our estimations. We introduce GFT ratio R, which is the ratio between sum of energy over low frequency to sum of energy over high frequencies. And we, through curve fitting, find that there is a connection between the precision and recall we mentioned before. There's a connection between them with the GFT ratio R. So how we evaluate estimate our accuracy, we will evaluating the curve fitting function output for specific graph Fourier transform ratio R that we obtain from the appliances service. And in PR estimation, we also use average number of high frequency components as a constraint to adjust to your final classification accuracy levels. So this figure shows a connection between the recall and the GFT ratio R, and the table here is comparison of our estimation with the ground truth from the submetered measurement. As you can see, most appliances we have correctly estimated only The washing machine for the house 8, it's not as good as we estimated, and the kettle in house 2. These are influenced by the few runs of the appliances in the testing data. Again, we can also use these estimations as a feedback to the NIM algorithms to improve your algorithm. In some case, and some private work has already done that, and it should be work for event-based algorithms. And I leave the final words to.
So thank you. So final words. Well, there is no single accuracy measure that captures accuracy of NILM. We want to be able to use a range of metrics, but they should all be kind of uniform. So having a toolkit or some sort to be able to accurately compare algorithms. We need to evaluate our algorithms at scale. We need to have sufficient runs of an appliance, at least a month or a long enough time in order to do that. And it has to be done on multiple datasets because performance varies significantly across appliances within a data set, across houses within a data set, obviously across sampling rates. So before we start any NILM processes, we want to be able to estimate accuracy prior to NILM. So this is what we propose, a quick, simple GSP-based NILM accuracy evaluation method where you only need to have one sample of your appliance running so that you can look at how it works and compare it in terms of your power usage. That's us. Thank you.